Hi everyone. In this video I want to talk about the Big Bang Theory, which kind of sits in this precarious spot between general relativity and quantum field theory. Since it's a theory of the universe, we expect general relativity to come into play in kind of the fundamental structure of space and time. But also, because we're talking about huge energy densities, we also expect quantum fluctuations and different things like that to play a significant role in the theory. And so, it kind of sits in this precarious spot between the two. On the other hand, that's also one of the reasons why physicists are so interested in the theory, because it may be a source of evidence for us to push beyond the standard model and find some way of unifying the two fundamental theories, general relativity and quantum field theory, into one massive theory of everything. So it's worth talking about and interesting in its own right. So there are four main lines of evidence for why physicists and astronomers have postulated the Big Bang. The first is the Hubble redshift, and that's just the basic fact. If you look at the stars, they're all moving, and on average they're all moving away from us. And the farther away you look, the faster they're moving. It kind of speaks to this explosive type motion. Also, there is the amount of helium that's in the universe. So if you look out and you say, how much hydrogen, how much helium is there? About 3-to-1 ratio. There's about 3/4 of the universe hydrogen, 1/4 helium. That's too much if the source of helium is just stellar fusion. Also, there is cosmic background radiation. So radio telescopes look through, do their investigations. At a certain frequency, there's this constant hiss, this hum. And no matter where you look, there's always this same level of hum. It's very uniform, and it's the uniformity that's the clue, because these areas of space are far away from one another. And yet, for there to be this kind of uniformity, there should be some sort of process that created this equilibrium. And that speaks to a much smaller universe in which that equilibrium could have been achieved. The fourth line of evidence, a little more subtle, is basically the large-scale structure of the universe. So, stars collect together to become galaxies, but the galaxies also collect together to become these larger clusters and also larger super clusters. This also speaks to kind of this issue of they're too far away for them to have really collected together in the way that they're collected. And so all these lines of evidence speak to a much smaller universe in the past, and hence the Big Bang. Now, as theories have been developed and progressed, the simplistic version of the Big Bang, where you just have an initial explosion and things just move out, there have been some issues. And so, over time, physicists and astronomers have created what I call the Big Bang 2.0 theory, also called the Lambda CDM model, in order to explain all the different pieces. But we do kind of have a basic theory in place. And this is the picture of what's going on. So, initially you imagine you start out with kind of this state of infinite density, which, kind of doesn't make sense, but you got to imagine that this is the starting point. And you have this massive inflation of space and time, and this is important for some of these arguments involving the uniformity elements or pieces of evidence. That this inflation occurs very quickly, and then comes to an end about 10 to the minus 32 seconds after this initial explosion. So very quickly, and then kind of the next phase occurs. And we move into a state where, initially the energy density is so high that, it's just quantum flux. You just have energy. It's just this big soup of quantum energy. But as, things expand, kind of from basic thermodynamic argument, as things expand, temperature gets reduced. And so, in a sense, the particles of nature, the 12 fundamental particles, the quarks and the bosons, start to freeze out of this huge quantum soup. And you start to actually get the creation of these quarks, electrons, neutrinos. Matter itself starts to form. And the electroweak symmetry starts to break, we start to actually generate a pure electromagnetic force. So the forces themselves start to manifest themselves in the way that we experience today. And eventually, what you have happening is that, the fundamental particles of matter start being created, and this is when nucleosynthesis would occur. And so here's where the helium would be generated, and basically the quarks start to condense, if you will, out of this quantum soup. They then form, initially they're so energetic that they're just bouncing around, but eventually they start to slow down, snap into the protons and neutrons. The protons and neutrons themselves snap into the helium that we observe in the elemental abundance I mentioned earlier. And then there comes a very important moment here about 380,000 years after the Big Bang, called recombination. And that's where the motion of the protons and the neutrons, the electrons, start to become slow enough where they lock together in the actual atoms that we know and love, hydrogen and helium atoms. And the reason that's important is because prior to that point, the photons in this quantum soup are all just kind of being absorbed by the charged particles. But now you have basically the universe, all the matter in the universe, all of a sudden becoming pairing together, and there's no charge at all. You have neutral atoms. And so all of the electromagnetic energy all of a sudden has nothing to react with. And basically you have kind of this, this explosion of energy, electromagnetic energy. And this is the cosmic background radiation that I mentioned earlier. And that's basically evidence or when the background radiation was generated, 380 years after the initial Big Bang. And the reason we can kind of get that timing is from the frequency of the background radiation and various things like that. And then much later, it continues on. And then about the first stars start to collect about 400 million years ago. And then you have the stars go through a process. They go through their natural life cycle. Some of them die. They die in supernovas. That creates the higher, more massive elements that exist. And so our solar system is actually a second or third generation star, because we've got a significant amount, or not significant, but we have enough of these heavy elements to actually create the matter, the 92 elements that exist on the planet. And so that brings us to about now, about 13.7 billion years later. The crazy thing about now is that we actually normally would expect this explosion to kind of be slowing down over time. But recent evidence speaks to the fact that the acceleration, detailed investigations into the Hubble redshift show that actually the acceleration is expanding. And this expansion really ought not be. And this expansion is kind of unexplained, what its ultimate source is. But it's called dark energy. It's the dark energy you may have heard of. And it's really this idea of dark energy is just another way of talking about this expansion that we're talking about. And so that, in a nutshell, is a history of the universe, and really brings our entire class to a close. So thank you for watching the videos.